Hello and welcome to the debugging point. In previous videos, we discussed about pointer arithmetic, in which we concluded that incrementing or decrementing of pointers makes sense only in case of array, because we know that on incrementing or decrementing a pointer to an array, will the pointer after modifications will land up to some memory location or some memory address which has been allocated to us by the compiler. It won't land on some random address on which we do not know what exactly are the access permissions, or is it having some important value for the operating system or not. Alright, so that's what we discussed. So let's begin the discussion for this video about arrays and pointers. So you see line number 6, this piece of code actually tells you, so how will actually the compiler compile this piece of code. Actually what happens is that a 40 bytes of memory is allocated to A, and this 40 bytes of memory is collectively called as A. What is A? A will actually have the array named A will actually have the address of starting of this 40 bytes. So what is the, let's say the starting of this 40 bytes address is 700. So 700 is the address from which these 40 bytes of memory has been allocated to A by the compiler. So this 700 is actually, or the starting address is also actually the address, the starting address for 0th index element of the array. Therefore, this is equal to 700. A will have the starting address, which is the 700, which is also the address of A of 0. Alright, I hope this concept is clear to you. So let's just try and run this code and let's verify if we have learned it right or not. So see, A and ampersand A of 0 comes out to be exactly the same number. So why is this happening? This is because when the compiler encounters this line, the 6th line, what exactly happens is that it takes 40 bytes of memory and allocates it to A, and A will contain the starting address which is 700 in our case. It will contain this starting address, which is also the starting address of 0th index element of the array. I hope it is clear to you now. Alright, so now you see A is actually having an address, and it is an array of integers. So can it act as a pointer to an integer? Now let's try to see that. Let's say we have A of 0 is equals to 100 and we see out star A. So what happens is that it also outputs, this line of code actually outputs 100. You see here? Alright. So what exactly is happening here? Actually the A has the starting address of these 40 bytes of memory, which is also the starting address of this first block, or the 0th block, I must say, the 0th integer. It is also the address of the 0th integer. So A will have the starting address of the 40 bytes of memory allocated, and it will behave as a pointer to the integer with the address of A0 stored in it. So when we do star A, it actually prints whatever is inside this very first A0 block. Alright, whatever is inside this A0 block, it will print that. We have made this value to be 100, so it prints out to be 100. It basically dereferences the value. Alright, so now we know that A acts as a pointer. Alright. So is there a possibility we do something like this? See out A plus 1. Since A is the uh, pointer to 0th element, so A1, it will technically be the pointer pointing towards the first element, that is A1. Alright, so if this is A, so A1 would be this, likewise A2 would be this, A3 would be this, and A4 would be this. So if I do A plus 1, so this would be A plus 1, and on dereferencing it, it would actually give the value whatever is stored inside this piece of block or inside this memory. Alright, so let's say we make A of 1 to be minus 5. So A plus 1 on dereferencing, that is star A plus 1, should actually give you minus 5. Let's see and verify. You see here, the first output, that is star A, was 100 because we had stored 100 in the 0th index, and on first index we have stored minus 5. So star A plus 1 is actually giving us minus 5. Alright. So A is nothing, but it is array. A is nothing. A is acting as a pointer, or very similar to pointer. It is not exactly pointer, which we will see in later stages. It is not exactly pointer, but it is resembling very closely to a pointer. So see, A was the starting address, has the starting address for 0th index. Likewise, A plus 1 will have the index for first element, A plus 2 will have for the second element, and likewise they will all have on dereferencing. We can get that particular the value stored in that particular index. You see, star A will give you A of 0, star A plus 1 will give A of 1, star A plus 2 will give A of 2, and so on. For any general ith element, what will happen? Star A plus I will give A of I, right? So A plus I is technically giving is a pointer which is giving the address of that ith element, and star is dereferencing that particular element. So we get the value stored inside it as the output. I hope this concept is clear to you. I'll be a little repetitive in this video. Now, this concept of pointers is actually what compiler is following when it compiles a code. Let me show you how. See, when you do A of I anywhere in your code, then actually what compiler does is it converts it into star of A plus I, and then it processes its command. So this thing is actually converted into this, and then it is processed by the compiler. Actually, we can also befool the compiler by this. If we do I of A, then what the compiler will do, it will actually convert it into star of I plus A, and then it will process it. So even if we do not do this A of I, rather we do I of A and then we hit run, then what compiler do, it will also convert it into I plus A, and then it will process. If so, effectively the same thing, absolutely the same thing will be processed. So let's try it out. I have already written the code, so let's just try and copy paste it here. So A of 0, as we know, is 100. Let's see what is the output of 0 of A. It should also come out to be 100, which is coming out to be 100. You see the last line of code, 100, 100. Alright, I hope this concept is clear to you. Essentially what compiler is doing in this line, it is converting A of 0 to star of A plus 0, and in this line it is converting it into star of 0 plus a, which is essentially the same thing. Alright. Now let us just talk about, so these were actually the similarities that we drew from between an array and a pointer. So till now we have seen that array is like very much, integer array is very much similar to that of integer pointer. But now we will realize that there are some essential differences that we need to know between them. Alright, so before discussing the differences, let me tell you that why will the differences occur and what exactly are those differences. Alright, see, we have an array. Let's say the array has a starting address of 780. Alright, so in the symbol table an entry would be made corresponding to an entry in the symbol table would be made corresponding to that of a, that a is an integer array and it has a starting address of 780. So these 40 bytes have been allocated to the array I, to the array A. Alright, now let's say if you have a pointer P, it is of let's say some address 891. So if we have initialized it, then corresponding to it, the entry in the symbol table would be made. P is int star type and it is at address 891. Now if P is pointing to the 0th index of this array, then P will actually have the address 780 stored inside it. Alright. Now you see the difference. The difference in A and P, that is array A and pointer P, is that pointer is pointing to the 0th index of the array A, but it has a different memory, an altogether different memory allocated to it. Alright, that means, but on the other hand, if you talk about A does not have a separate memory in which it has stored the starting address of this memory. Alright, this 40 byte memory. It is not the case. See, the value of A is directly obtained from the symbol table. If you're getting confused, then give me some time, you will understand it. Alright. See, when we have initialized our array here, let's say int a10, and we have initialized int star p, int star p, and we made it ampersand a of 0. Alright, so in the 6th and the 7th line, what essentially are we doing? We have initialized an array A. So corresponding to it, an entry would be made in the symbol table. So how the entry would be made? An entry that int A is an integer type array and it has a starting address of 780. This address has been taken hypothetically. Likewise, we will have a pointer P and it would be of type int star and would have a starting address of 891. Alright, now P is pointing to ampersand A0, which is the 0th index of the array, 0th element of the array. So now P is pointing to this. P has the address of this, that is P has 780. A, the value of A is also 780. We have shown this earlier. Cout A gives us the address of A. Here, the topmost line. Let me zoom it for you again. this one, the line number 8, the first cout statement. See, the ampersand A of 0 and A are exactly the same, which means that A also has the starting address of 0th index and P also has the starting address of the 0th index. But P has a separate memory in which that address has been stored, whereas A does not have a separate memory. When we cout A, what compiler does, it checks through the symbol table and sees the value corresponding to the address corresponding to A, which is 780, and simply prints it. Because on that address we have an array and cout cannot print an entire array, so it prints the address. Alright, so A has an address, the value of P is also an address, but A does not have a separate memory to store that address. It is obtaining its value directly from the symbol table, whereas P, which is the pointer, has a separate memory which has of 8 bytes which has been allocated to it by the compiler, and inside that memory it has stored the value 780. Alright, this is the basic difference. This is the basic difference which I am trying to convey. Now if you are still confused, please hold with me for some time. I'll clarify it again. Now see, let's talk about the differences. Let's talk about the first difference. You see, the size of int A 10. If we do size of A, so what would be the size of A? It would actually be 40 bytes. And the size of P would actually be 8 bytes. So why is this happening? See, when we do size of A, it will go through the symbol table and check it's an integer array. So it has been allocated 40 bytes. So its size is 40 bytes. And P is a pointer. It has been allocated 8 bytes of memory by the compiler. Hence its size is 8 bytes. So A is acting as a pointer, but it is not exactly a pointer. I hope you are getting what I'm trying to convey. Now let's draw the second comparison. The second comparison is, see, if you have A, you have P. Alright, we have discussed this. It has the value 780 stored inside it. Alright, now if you do A, the compiler will look through the symbol table. As soon as it finds A, what it does is that it goes to that memory. It sees that as soon as it finds A, it sees that A is an integer array. It is not simply an integer variable, rather it's an integer array. So since it is an array, so the compiler cannot go to that memory address and fetch the entire thing. It rather simply prints the address, whatever was written alongside integer array. Alright, whatever was written inside the symbol table. However, when we do cout P, what happens? It looks to the symbol table, it sees that it is a variable of type int star, which is also a pointer. It sees that it is at address 891, so it goes to that address and it fetches the value and prints the value. So if you do cout A, what is going to print? 780 is going to print. And when you do cout P, what is going to print? Again 780 is going to print. But if you do cout of ampersand A, what happens? You are going to check for the address of A. So by default, you check through the symbol table and whatever is written for the ampersand one, whatever is written in the symbol table, you print it as it is, because you assume that that is the address. Likewise for P, you check through the symbol table when you say cout, we have to cout ampersand P. You check through the symbol table, you find P and you see the address corresponding to P and you simply print that address. Alright, so something very common has happened for variable p, and something very uncommon has happened for array A. See, A is an array and it has been allotted a chunk of memory, say 40 bytes of memory. Alright, and an entry corresponding to it has been made in the symbol table. So when you do cout ampersand A, the very usual thing happens. You check through the symbol table, whatever is the address, you print that. Similar is for the pointer P. Whatever is the address, you go to it and print that. But when you do cout A for the array, what happens? You check through the symbol table for A, you find A, you see that it is an integer array. It is not simply an integer variable or an integer pointer. Since it is an integer array, so it is supposed to have many elements at a time. Since you cannot simply have many elements assigned to a single name, assigned to a single entity, you cannot have many different values. Therefore, the compiler has been designed, or the documentation for the C++ is written in such a way that A will actually have this very thing, the address at which it is located. Hence, the address for A, the value of A, both come out to be exactly same, which is also similar as that of ampersand A of 0. I hope this is now a little bit more clear to you. Let's move on to the third difference. Hopefully this will clarify it further. You see, the value of A comes directly from the symbol table. The value of P does not come directly from the symbol table. It rather comes from a memory location which has been assigned by the variable, which has been assigned by the compiler to this particular P variable, which is also a pointer. Alright. So let's see now the third difference. See, if you have P is equals to P plus 3 and you do A is equals to A plus 3, so this is okay because see, P is this value. You do, when you write P means this value which is inside this piece of block, this piece of memory. So you can overwrite it by, say it was 780, it will go 4 ahead each time, so it will become 792. By plus 1 it will become 784, then it will become 788, then it will become 792. So this value becomes 792. But the value of A comes from the symbol table, and once an entry has been made in the symbol table, we cannot change it. So the value of A comes out from the symbol table. We can read it, but we cannot change it. So this is absolutely invalid. The compiler will throw an error if we try to do such a thing. Alright. This is because the value of A comes directly from the symbol table and nothing can be changed from the symbol table by the coder or the programmer. Alright. I hope it is clear to you. Again, let me give you a quick recap of what has happened till now. See. What happens is that you have an array. You have written int A 10. You have written this statement int A of 10. Alright. So it will allocate 40 bytes. The compiler will allocate 40 bytes of memory to you in the name of A. Alright. Now, corresponding to this allocation of memory, an entry in the symbol table would be made saying, yes, or specifying that A is an integer array type and it has a starting address of 700 in this case. Alright, this address has been taken hypothetically. You can take, it can be any address. Alright, so if you do cout a, if you do cout a, so what will happen? The compiler will actually look through the search through the symbol table. When it finds a, it sees that c, it is an integer array. So you cannot really have so many values. You see, integer array is having multiple values. All right, so corresponding to this, you cannot really print or you cannot really return multiple values corresponding to one name. All right, one name. So what the documentation says is that for this very particular reason, for this very particular case, 700 or the address itself is returned. So if you do cout a, the answer you will get is 700. That is nothing but 700. If you do ampersand a, then it will again search through this, and ampersand a again, for ampersand a as well, the address is returned. Alright, and this 700 and this 700, which means the value of a and the address of a is absolutely the same thing, which is also equal to the address of 0th element of the array. I hope the concepts are a little bit more clear to you. If they are not, then just watch this video once more. It will lead to a more clarity. Thanks for watching. Please like, share, and subscribe my channel.